In this section, we're going to be taking a look at rational functions, which means fractions with x's, with polynomials in top and bottom. So one of the interesting things about rational functions is that there are oftentimes values of x which have to be excluded from the domain. For example, if y is equal to 4 over x, x cannot be 0 because there's no such thing as 4 divided by 0. So anytime the denominator is 0, we have to exclude that number. Now the easy thing about dealing with rational functions is we can use our calculators quite easily. Now here's what it would look like if you typed 4 over x on your calculator. Let me remind you that you have a fraction key that you can access by using the alpha and the y equals key. So typing 4 over x and then hitting the graph button, we get a graph that looks like this. You can see on this graph that indeed here where x is 0, which means the y-axis, there's no graph. So that is not a value in the domain. You can also see here that we have values of x everywhere else, just not in the domain. So the domain of this function then would be all values except for 0. Now there's many ways of saying that. In your homework, they're going to want you to use interval notation. So we say this by going negative infinity comma 0 with a parentheses here to indicate that 0 is not included. And then 0 comma infinity. So that's what our interval notation would look like for the domain. Now the other issue about this is the range. So to do the range of this function, we can obviously look at the calculator again. You'll get some ideas from just what we do with the calculator on how you can answer these if you don't have a calculator. However, you notice here also that the blue graph goes along the x-axis forever, but never touches it. So, like the domain, 0 is not in the range. You see this goes up forever, this goes down forever, and so you can have all values except for 0 also, which means the range would, in this case, mimic the domain. You can tell by looking at the fraction itself that the numerator can never be equal to 0. So 0 is not in the range. So before we even touch our calculator, do you see that for this one, since the bottom of the fraction is x minus 3, we know that x cannot be a 3. And so I bet when we graph it, we will see such a thing. Now what the rest of this looks like is kind of blurry to me right now. But if we take a look at the graph, here's how we would type this. And then here's the graph of it. You can see reflected again what we just got through saying. Here is 3 on the graph. There is no value here or here. So there's no value at 3. There are values from negative infinity to 3. There are values from 3 to infinity. There's just no value at 3. You can tell the range from looking at the graph is going to be the same as the previous problem. Negative infinity to 0 and 0 to infinity. So again, look at the blue graph. It levels off along the x-axis without ever actually crossing it. And again, you can look at the numerator and tell it's never equal to 0. Now this one has lots of stuff going on, but just like the previous ones, I can tell just by looking at that you cannot have a 3 for x. Here's the graph, and sure enough, here is 3. No value anywhere above or below x equals 3. So the domain of this is just like the previous one. We can go from negative infinity to 3, from 3 to infinity, just not the 3. Now the range is a little trickier. You can see here that if the blue graph is coming down, it starts leveling off. Now the question is, how low does it go? Well, you saw from the previous problems that normally this thing, since the numerator cannot be equal to 0, normally this would level off at y equals 0 or the x-axis. And we know this minus 4 tells us it's shifted 1, 2, 3, 4 units down. And so the range would be from 4 to infinity. Notice there's nothing below the line y equals 4. Well, a little off on that, but you get the idea. So we've been talking about the values of x that give no answers. There's a special name for that situation: asymptotes. The term asymptote literally means that it gets close but does not touch. That's the meaning of the word from Latin. So anyway, if we draw the graph of this, you'll get a better picture of what's going on. There is a special line right here where the blue graph gets closer but doesn't touch it. There's also one right here. Now these, you recognize, are the numbers that don't work in the domain. If I take a look at a table of values, I see exactly what those two numbers are. That would be -2 and 3. So we call these vertical asymptotes. And x equals -2 is the equation of this vertical asymptote, and x equals 3 is the equation of this vertical asymptote. There's also horizontal asymptote. You notice on this that the blue line comes up but never touches the x-axis. The blue line comes down but never touches the x-axis. That's called a horizontal asymptote. Now its equation would be y equals something. Now the x-axis happens to be y equals 0. Now I'll show you how to recognize vertical asymptotes without even typing anything on the graph. Vertical asymptotes are going to occur where the denominator is 0. So we could take x squared minus x minus 6, set it equal to 0, and solve for x. You could do that on this one simply by factoring the x squared minus x minus 6 into x plus 2 and x minus 3. That would give x equals negative 2 and x equals positive 3, which happens to be our vertical asymptotes. And here is how you can tell horizontal asymptotes. If you look at the relationship between these first two terms, the x to the 1 and x to the 2, since the bottom exponent is bigger than the top exponent, it's always going to be the x-axis, or y equals 0. Now I'll show you this one without even using a calculator. And you can do something similar on the first one. Just repeat what we're doing right here. I'm looking at this x plus 1, and I'm thinking if x plus 1 was a 0, then x would be negative 1. So that right there is what's called the vertical asymptote. Likewise, we can look at just these front two terms, 4x divided by x. Since the exponents are the same, we can divide the coefficients to find the horizontal asymptote. 4 divided by 1 would be 4. So let's try that again. When we're looking at the x minus 1, if x minus 1 were 0, then x would be a 1. That is the vertical asymptote. If we take these two terms, the top has an exponent of 2, the bottom has an exponent of 1. If the top exponent is bigger than the bottom exponent, then there is no horizontal asymptote. Since most of you are using the graphing calculators, I will be doing this from the graphing calculator. Let me mention, however, that even without a graphing calculator, I can get a pretty good idea of the graph. If I take the bottom, x squared plus 6x plus 9, set it equal to 0, and solve for x. This factors into x plus 3 and x plus 3. So x equals negative 3 is the only vertical asymptote. If I look at the first terms, since they both have an exponent of 2, we can divide the coefficients, 2 divided by 1, which is y equals 2. That is the horizontal asymptote. Now I'll just get you started on the graph. Here is a typical graph. If we put a vertical line at negative 3, that would be our vertical asymptote. If we put a horizontal line at y equals 2, that would be our horizontal asymptote. Now, let me point out that a horizontal asymptote is only an asymptote in the sense that the line comes out at the end of it. So, if I were to choose a number, for example, here's negative 3, this would be negative 4, negative 5, negative 6. If I take a number like negative 5 and plug it in place of the x, 2 times negative 5 squared plus 3 times negative 5 minus 4 over negative 5 squared plus 6 times negative 5 plus 9. Now I'm going to spare you all the details of doing that calculation, but you get the point. Plug it in and see what you get. Now this comes out to be a positive number. In fact, it comes out to be above the green line. It has got to curve up along the blue line. I'll let you finish it from there, but you can come out with the rest of the graph, something similar to what I just did. However, like I said in the beginning, I would prefer to just type it into my calculator and hit the graph button. So you can actually see now what the remainder of this graph is going to look like.